All right, hello there, and welcome to Data Communication and Networking Weeks 8 and 9. So, today we're going to be speaking about four main topics: data link layer, the network layer, and routing protocols under the network layer, and the transport layer. So, without further ado, let us get right into it. So, first up, we're going to talk about the data link layer. So, the data link layer works with frames, okay? It works with frames, and essentially it is used to, obviously it is something that encapsulates data and decapsulates. One of its main functions is including the MAC address of the device. And the other thing it does is it detects collisions. And last but not least, it does an error checking using the CRC, or cyclic redundancy check. Okay, so let us talk about MAC address. Now, first off, we should know the difference between MAC address and an IP address. A MAC address contains 48 bits, whereas IP address contains 32 bits. Okay, MAC address is unique to every device, whereas IP address is assigned by the network to a device. So you may be able to change the IP address, but I don't think you are able to change the MAC address of a device. Okay, so why does it include the MAC address? What is the point of including the MAC address? Well, using this, what it can do is it can find the specific device inside of a network. That is one of the main reasons why the MAC address is included in the frame. So let us we will come back to the MAC address and how all this connects, but let us move on to collisions. So when data moves in the in opposite directions, it can collide in a half duplex system, right? Because in a half duplex, only in one direction at a time, right? Hence why collisions happen. And any part of a network where a collision can occur is known as a collision domain. Now let's say that this is a hub. Then this entire network is a collision domain. So hubs are basically used less nowadays, but it does have its uses. Okay. So how does the link data link layer help here? Well, it does help avoid collisions, not avoid, I believe, detect collisions by using the CSMA CD, which stands for Carrier Sense Multiple Access Collision Detection. How does this work? Well, basically, old connections used buses, right? So what it would do is it would check if the line is idle or the system is idle. If it is idle, it will send the data. If it is not, it will deter the sending or stop the sending process. So let's say two devices send at the same time and a collision occurs. Immediately, a jamming signal is sent to all other devices, and then the two devices that sent will resend after a random amount of time. So device A will send after X and device B will send after Y amount of time. So that is how CSMA CD works. Now that is basically only used in half duplex systems. When it comes to full duplex systems, this entire thing can be avoided because data can travel in two directions at the same time. And you may be like, okay, but what if C sends to A and B sends to A at the same time? We will get there. So to solve that problem, we improve to switches. Now, switches have a specific way of solving problem, but its main thing is to store and forward packets, right? And a switch also learns the system. So it can either specifically forward to the devices or it can flood. Here's how a switch learns in a system. Let's say there is a device A connected to port 1, a device B connected to port 2, a device C to 3, and D to 4. Let's say A sends a packet to D. The switch will store the MAC address of A to the port 1. But since it does not know the MAC address of D, it will flood to every other device. Now, how does C know that this packet is not to it? Well, it will cross-reference with the destination address. And it will be like, okay, fine, this is not for me. And it will discard the frame. So, now D again sends a message back to A. This time, because the switch has stored the data A, stored the device MAC address A is coming from the number 1 interface number 1, it will not flood, but it would specifically forward data, specifically forward the frame towards A, right? So that is one of the main reasons why we use switches. Now, every single switch does something called auto negotiation with every single end device. What does it mean? Well, that means it and the device, both of them will decide what speed to run on and what duplex mode to run on, right? And at the same time, in this system, you might be like, okay, isn't this each having different collision domains? Well, if there is a singular connection, that means that it is not a collision domain. Collision domains cannot occur. So another main reasons why we use switch is to reduce the amount of collision domains in a network, right? Okay, so there are different MAC protocols for different wires, right? So let's say there is something called 100 base and TX, okay, or T4 or T2, and then there's SX, then there's FX, and then there's BX, so on and so forth. What I do know is that this indicates the speed, so it's 100 megabytes per second. Base stands for base band. T stands for twisted pair, and 4 means 4 pairs, and 2 means 2 pairs. Whereas this is for optical fiber optic cables, whereas this is for copper, right? So let us move on to how wireless networks avoid collision. So I hope you noticed wireless networks avoid collision. Why is that? Well, because wireless networks, the medium is air. If any collision occurs, it cannot like verify whether it actually occurred or do anything with it. So it avoids the collision altogether. One of the good examples for this is the four frame handshake, right? One of the good examples for it. It connects and then connects. It does an RTS, then it does a CTS, and then it sends the data, and then it finally sends an acknowledgement, right? So this is one of the main reasons CSMA CA why wireless networks do not have collisions, and this is also run by the link layer. So let us move on to another very important topic: VLANs, virtual LAN. Now, the definition for virtual LAN is to reduce broadcast domains, increase security and administrative efficiency. So, what is a VLAN? Well, basically, you can take a switch that has 16 ports and you can divide it and be like, okay, 8 ports are for IT devices that are for the IT section, and 8 devices are for the HR section, right? So basically, you're switching a single switch into multiple virtual switches, right? So when you connect, right, more than one switch with VLANs on it, what you must do is it is called intra VLAN or inter VLANs. When you connect more than one switch with VLANs, all of it connected together, what you must do is you should also have something called a router on a stick connected to at least one of the switches. Why is that? Well, it is used so that sometimes whenever you want it, an IT device can speak to an HR device, or from a VLAN of 1 can speak to another VLAN of 2, VLAN I. So in Cisco Packet Tracer, whenever you go to a switch, you can always make a VLAN. So the way you make a VLAN is you first of all enable in the switch, then you go to config terminal, and once you go to config terminal, you can type in VLAN, and you can type in your ID, then you can say name, and you can type in the name of the VLAN. So for instance, let's say ID1 is going to be IT, then you can exit. So you can keep on doing this on and on to assign VLANs, IDs, and names for each of those VLANs, right? So when a switch is connected to an endpoint, right? It is connected using an access port. Whereas when a switch is connected to another switch, it is connected to a trunk port. Now, why is this? Well, if you're going to connect physically, you don't have to you obviously have to assign each and every single one of these ports to the specific VLAN. But when data travels from switch to switch, How will it know what VLAN it is the data belongs to? So that is why we trunk port it from a VLAN switch to another VLAN switch. So the way you put access port is you write interface and you write the interface number. It's usually fast Ethernet 0 and a number. Then what you should do is switch port, port mode access. Then you put switch port access and then you give the VLAN ID. So it's 1. And after that, what you can do is you can exit and you can keep on doing this on and on and on for every other port, right? Every other interface basically. But when it comes to trunk, you put switch port mode trunk and that's it, right? So all you have to do is connect to devices. Sorry, connect to switches. So what does a trunk port have? Well, it basically has the 802.1q encapsulation data, which we will assign in the router. So we have to go to the router. We have to go to the config terminal in the router, and we have to type in the interface where it's connected to the stick. So interface, and let's say it's connected to FA08. I don't know why specifically is connected to that. Then what you must do is you must write encapsulation 802.1q, and then we must write the VLAN ID, right? After that, what we must do is we have to write IP address, and then here we must write is the default gateway and the subnet mask. So the frame format when it comes to here is like this. So there will always be something called a preamble. This is not part of anything. It's essentially like a wake up call to every single device. Then there will be the destination address. Then it will have the source address. Then here is something called type, where it will say what type of packet this is. So is it IPv4? Is it ICMP? Is it an ARP? So on and so forth. But along with this type, it will include the 802.1q tag. It will have the TCP and TCI and TPID. So TCI stands for tag control information, and TP stands for transfer protocol ID. Sorry, track protocol ID. So these are things that will be included in the 802.1q VLAN tag, right? So after this, there will be the data or payload, and finally we will have the CRC, the error checking. So this is how all wired devices connect. But now let's talk a bit more about wireless devices. Right, we have space down here. Wireless devices use something called an AP or access point. Now, an access point basically allows wireless devices to connect to a wired LAN, right? It allows wireless devices to connect to a wired LAN. Now you may be like, okay, but what is the access point in my home? What is the access point in my Wi-Fi router in my home? Well, basically, a device connects to an access point which connects to a router which connects to a modem. Modem stands for modulator demodulator, the more you know, which connects to the ISP. Now, in most of our cases, these three are all combined in one single Wi-Fi router. But let's say for some weird reason you haven't paid your Wi-Fi bill. That means there is no data, but the Wi-Fi is working. Well, you can utilize the access point in there to send data, to transfer data between devices, right? So essentially what you're doing is you are utilizing the access point to transfer data between wireless devices. You're using your Wi-Fi router as just another route. So how does an access point work? Well, there are two ways. One known as passive scanning, and the other one, which is the more realistic one, active scanning. Passive scanning is the access point sends out beacon frame, right? Sends out beacon frame. What's a beacon frame? A beacon frame will include information, something like SSID. The SSID means the name of the network, name of the access point. Then BSSID. So BSSID is like the MAC address of the AP radio. Let me write that down here somewhere. Of AP radio. And then last but not least, it will include channel and security information, right? So this is what the beacon frame is. So once it sends out a beacon frame, the device, after it gets the beacon frame, it sends out an association request. The AP sends out an association response, and then the device is connected. And then there is a rudimentary form of authentication. So authentication is not something like a password. It is basically like you know a way to like say, okay, we both can communicate. So that is basically what authentication is. When it comes to active scanning, it's a bit more nuanced than that. So the device doesn't wait till the access point sends out a beacon frame. What it does is it sends out a probe request. Now it can be of two types. It can be either a null probe request, or a direct probe request. The null probe request means there is no SSID in the probe request, meaning any Wi-Fi network will be getting the request. Whereas direct has an SSID. So it's sending a signal directly to one specific access point. And then the access point responds with a probe response. I know, sounds cliche. So the probe response is basically the beacon frame. It sends out the beacon frame to the device. And then again, device association request and then AP association response happen. So that is most of it. I believe there's one more small thing to talk about, which is MAC protocols in wireless transmission. Now we learned about MAC protocols in wired media, the 100 base, TX, T2, T4, SX, FX, BX, all that stuff. So most wireless transmission is half duplex. You may be surprised to know this, but most of your Wi-Fi is half duplex. And because sometimes they may use separate channels, right? So if they use separate channels at the same time, they can get it close to full duplex, but it's never really full duplex. Okay, it's always half duplex. So the wireless 802.11, so there's A, there is, I believe, N, AC, and AX, stuff like this. So there are two main protocols in the wireless transmission MAC protocols, which is PCF, point coordinated function, the less realistic one, and DCF, distributed coordinated function. Point coordination function is the access point decides which device to transmit. So who transmit, right? So it will like decide, okay, at this moment you have to transmit, at this moment you have to transmit, at this moment this you have to transmit. And it is less reliable, it is, not practical. Whereas distributed coordination function, the devices contend for transmission space, right? So they can fight aggressively or they can, uh, fight politely. So this is PCF and DCF. So that is the link layer done. So let's talk about the network layer. So the network layer is mainly about the router. It always comes up with on the router, right? So the network layer works with data, right? So the router has two main functions. It forwards, forwarding, and routing. So forwarding depends from router to router or interface to interface, right? So to forward from one interface to another. So it's interface to interface. Whereas routing is done from source to destination, right? So the protocol that the network layer mainly uses is the IP protocol. It's the IP protocol, all right? So the problem is the IP protocol is unreliable. It's unreliable. It's best case, meaning it'll drop packets if buffer is full. That's buffer, not butter. And delivery is not guaranteed. So it has two helping protocols. The ICMP protocol that is used for error reporting, and the ARP, address resolution protocol, that is used to find all the MAC addresses on the network. Okay, right. So this is the main thing about the network layer. So we're going to be talking about the version, the frame format of the datagram. Okay, so I want you to concentrate. Very first thing we have is something called version, VER. So it can be version IP version 4 or IP version 6. IP version 4 is 0, 100, and IP version 6 is 0, 110. Right? Okay, next we have IHL, which is header length. IHL. So the header length can range from minimum 20 bytes, it's minimum 20 bytes, to maximum 60 bytes. So it can have 40 optional bytes. And this something has known as the header length value, which is basically the total value divided by 4. So the minimum value will be 5 and the maximum value will be 15, right? So this is the header length value, and this is how it's represented using the IHO. Next, we have something known as the TOS, type of service. The type of service. So the type of service has A, C, D, E, F, G, H. So this is how I remember it. So it has 1, 2, 3, 4, 5, 6, 7, 8. 8 slots, 8 bits basically. And the first 3 bits range from 0 to 7, and it tells the priority of this. The next one is a 0 or a 1, and it tells whether there's a delay or not. The other one is also 0 or 1. It will show us whether it has high throughput. And this also has 0 or 1, whether it says whether it has a high reliability. So 0 to 7, well, it could be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, so on and so forth, right? And finally, we have the length. The length is the length of the header and payload, right? It has both the header and payload. So to find the payload, we should take the length and subtract the header length from it. So next we have a 16-bit identifier, and we have flags and a fragment offset. Now first ask ourselves the question, why do we have this? Why do we have this? Well, let's say that the datagram size is X, but it goes through a point that has a maximum transfer unit that is less than X. What does it do? Well, basically, the protocol breaks this down into smaller pieces, X1, X2, so that it can go through the maximum transfer unit. And this process is called as fragmentation, right? So defragmentation occurs only at the final part or the destination. Defragmentation occurs only at the destination. So it's not like when it passes through the MTU, it will automatically start defragmentizing or making it up. No, it will waste basically space. So let's say it goes through an MTU of Y, and Y is less than X, right? So it breaks into X1, which is basically Y. This is an ideal scenario. And then it goes to another MTU, which is equal to Z. And Z is less than Y. Well, what will happen is, again, X1, X2, and so on and so forth will be broken into XA, XB, and so on and so forth. And all of this will finally be re-defragmented or defragmented at the end. So that is the entire point of having this. So the 16-bit identifier is like the 16-bit identifier is like the, how do I say this? It's like the, unique thing for each and every single one of these packets. So every single one of these broken ones. So here we have X1 and X2. And here we have XA, XB, XC, XD. All of this will have the same 16-bit identifier so that they can be all put together. But the thing that will differ from each and every single one of them is the headers. Each of them will have a separate header. So as you can see, this already has a header. But when you broke it into, these will get separate headers. And now when these are broken, these will get also separate headers. I want you to remember this concept because then only we can do the calculation a bit more easier. Okay. So How does it work? Well, it uses two types of main flags. The df flag, which means do not fragment. Usually this is set to 0, but if it is set to 1, that means it says do not fragment this datagram. Next, there is mf, meaning more fragments. If it is 1, that means yes, there are more fragments that are to come, and if it is 0, that means there are no fragments. So if, let's say that this MTU is equal to X and it doesn't break, then this one's MF value or more fragment value will be 0 because that is the last fragment, right? And next one we have fragment offset. Now, for this we need a specific example. So let's say that the datagram length is 4000 bytes, right? This is the datagram length. So the MTU that it goes through is 1000 bytes, right? Oh, yeah, it's 1000 bytes. Now, this is the entire datagram length, by the way. This is the value that will be in here, the length. So what we must do is we must find the payload. So 4000 minus 20. If they do not specifically mention the header length, we must take it as 20, right? Which will give us 3980 bytes, right? So here you have to see that the maximum transfer unit is 1000 bytes. 1000 minus 20 will give us 980 bytes. This is how much, how do you say? This is only we have to focus mainly on the data, right? So what we must do is we take 3980 and we subtract 980. We get 3000. We do another 980. We can go on and on. And basically, this is going to be your first fragment, second fragment, and you know what? Why not be, sorry. So 3000 minus 100 is 980. That's going to be 220, right? Then we can subtract 80. So that's going to give me a 40. That's a 10. So I'm going to again get a 9, 140. So this is your third fragment, and your fourth fragment is 140. So what is the fragment offset? Well, the first value has 0 to 980 bytes, right? And the next value has 980 to, well, this one plus 980. So how much is that? 80 plus 80 is 0, 6, one balance, 9006, so on and so forth. So you take the first value of these numbers and you divide it by 8. This is the fragment offset for the very first, fragment. The second fragment, you take 980 divided by 8, and so you'll get 1, and 18 has 2, that's 60, and then there's, I believe it will have a 20 here. Yeah, so in 20 there is about, yeah, 2, 1, 2, 2. So again, then you have 1960, and then you divide 1960 divided by 8, and you get the value. That will be the fragment offset. Why do we need the fragment offset? The fragment offset is used to find the order between all of these specific fragments, right? So that is basically the fragment offset and all that stuff here. So and then we have, after that we have the three main parts. The time to live, we have upper layer, and finally we have header checksum. So TTL is basically the number of routers that this datagram can go to. So for each hop, the TTL value decreases by 1, right? So why do we have a time to live value? Well, it is to stop datagrams from looping the system indefinitely and causing congestion and all that stuff. Upper layer has 2 to the power 8 bits, whereas each of these bits specify, okay, this is the, protocol from the upper layer that we are using. This is, all that information will be stored in here. And header checksum will basically check, make a mathematical check, and it will change from every single hop because the TTL value decreases every single hop. Next, we have the source IP address, then we have the destination IP address, we have something called the options, if there are, padding, and finally we have the payload. So this is the things that are mainly in this section. So let us move on. So let us now move on to IP addressing, the main part done by the network layer. So why do we need IP address? It is used to identify a network interface, right? That is the whole point of using an IP address. So what is an interface? The interface is a connection point of a router or host to a physical link, right? It's a physical link. So routers have many interfaces. So interfaces are basically like the port, the place where you plug in stuff, whereas end devices have maybe a maximum of 3, right? Okay. So now let's talk about the IP address. An IP address has 32 bits, right? But what we do is the 32 bits are separated into 8 bits, separately, right? 888. So essentially, what we do is we convert each of these bits into decimal number, and we put this in a decimal notation, which we call the dotted decimal notation. So this is an example for an IP address. We use the dotted decimal notation, right? So IP addresses have something called a host configuration. A host configuration has an IP address, a subnet mask, and finally a default gateway, right? So let's talk about each and every single one of these. So first off, why do we need a host configuration? Well, a host config is used to communicate with devices within and outside of a network. So host config is used to communication between devices within and out of a network. So let's talk about the parts of a host config. The IP address. So as you know, IP address has bits. So let me draw all ones. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this in decimal number is 255. 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 Now you might be like, hey, 2 to the power 8 is 256. So what happened to the 256th value? Well, 0, 0, 0, 0, 0, 0, 0, 0 is also a value. That is why this is the first value. That is why we have 255 different things. So an IP address is like this, and a subnet mask, right? A subnet mask is used to define the network part of the IP address and the host part of the IP address. What does it mean to have a network part? Well, that now basically it's like saying, okay, for instance, let me take this subnet mask 255.255.255.0. As you know, then this entire thing will be 0 and these will be 1s, right? So what we will have to convert them back into their decimal form, binary form, and then multiply the IP address. So any ones in here belong to the IP address over here, right? So that's a very important part. So why do we need a network part and a host part? Well, it's because so that it is easier to determine which network to send, and then the network will determine which host to send the data to, right? That is the entire point of a subnet mask. Finally, we have something called the default gateway. So let's say there is no place to send, or the IP address some match or something like that, then it will send to the default gateway, which is usually 000. And so most ISPs use this one as their default gateway, right? So let's talk a bit more about IP addresses and subnet masking. Right. So let's say you have the IP address, say 192.0.2. So 192.0.2.128. So this is the IP address, right? And they have put something called /27. What does /27 mean? It means from 27 bits from the left side are reserved for the network, right? So 27 means, so 8 plus 8, that makes 16. 16 plus another 8 makes 24. So 24 means 3. So that would mean 255.255.255, because that's all the 8 bits, dot the 3 values here. So that would mean 111000000. This is the last part, meaning these 3 numbers over here are reserved for, these 3 bits over here are reserved for the network, whereas only 5 values, 5 bit combinations are reserved for the host. So I think I realized my mistake. So it's 1, 2, 4, 8, 16, 32, 64, and 128. So this would mean 128 plus 64 plus 32, right? So that's going to make a 4. I'm going to have one more over here. So that's going to be a 9, 10, 12, one more balance. And that's going to be a 2, 2, 4. So this is the subnet mask of this value. So what does that mean? Well, that means that 2 to the power 5, there are 2 to the power 5 host addresses that can be used for host. But can all of them be used? No. 2 to the power 5 minus 2 are the only host addresses that can be used. Why is that? Well, you always have to separate one address as the network address and another address as the broadcast address. So network address is the very first address and the broadcast is the very last address. Now let's talk about this one. Here it is 27, right? So 32 minus 27 is equal to, I believe it is 5. That means it's 2 to the power 5, meaning that is 2, 4, 8, 16, 32. So this system is broken into blocks of 32. So that would mean 192.0.0 to 32, sorry, not 32, 0 to 31. Then it's 32 plus 31, well, it's going to be 63. Then it's going to be, oh, I believe this is 96. So that's going to be a 95. It's separated into these blocks, right? This is blocks. When it comes to the network address of this block, it is 0 and the broadcast is 31, right? Now let's go to the one we have. We have 128. So 128, I believe, will fall somewhere here. So that's going to be 8, 28. Ah, look at that. So 128 is going to fall here. So the network address of this specific one is going to be 192.2. Sorry, not 0. It's going to be 128, right? So this is a network address. This is a network address. And the broadcast address of this is going to be, well, if I'm going to add a 2 here, that's going to be 0, balance, 3, 160. So that's 159. So the broadcast address of this set is going to be 0, 159, right? So this is how IP addressing works, right? You have to split it into equal parts and each block size will be 32. So I'm going to link a few videos that I learned about IP addressing. They will explain it much more clearly than I have. And there are some things called broadcast addressing. There's some things called uh, broadcast address, reserved address, a few reserved addresses specifically for a few things. And last but not least, there are something called IP address classes, where class A is -8, class B is -16, and class C is -24. It is obsolete right now. That means we don't use it, but they may ask questions on this. So I hope you can learn up a bit more on this. I will make probably a short form video explaining class address, class IP address class. So that is all there is about network layer. We are so close, right? So we should mainly study next time about routing protocols. So I'm going to make a separate video for this because already this has taken so long. And anyways, good luck and have a great day.